Okay, so we're gonna do some stuff with radicals. Radicals are rational exponents, so a lot of these properties all just come from, or all of these properties just come from the properties of exponents that we know, just applied to, written in the notation of radicals instead of as explicitly as exponents. This is really just the definition of a radical, but if I were to write it in its exponential, like sister equation, this would say that a to the n raised to the 1 over n power is equal to a. And that should be true, right? Multiply the exponents. This says that a to the 1 over n times b to the 1 over n is equal to ab to the 1 over n. That's true because we can distribute an exponent over multiplication. The radical side of that statement is that we could split up or combine a radical under multiplication. This one, let's see, the mth root of the nth root of a. So this says if I have a to the 1 over n and I raise it to the 1 over m power, well, if we multiply the exponents like we know we're allowed to, we get 1 over nm, and that is the nmth root of a. And last, we can split up or combine radicals under division. So this is the one that says a to the 1 over n divided by a to the 1 over, b to the 1 over n is a over b to the 1 over n. Of course, we require that b not be equal to 0 in order for the operation to be defined. So these properties, they look different when written in the radical form, but they're properties we already know. Because we know that radicals are just exponents written in a different way, we know that we had better not split up radicals over addition or subtraction. So resist any urge you might have. We've been resisting the urge to split up radicals over addition since last semester when we were doing all like the Pythagoras and SOHCAHTOA stuff, right? Anytime we even work with a right triangle, we have to resist that urge. So we're getting very good at it now, right? Okay. So we're going to simplify some radicals. We're going to do this particular radical twice. And we're going to do it one way, sort of using explicitly one of these properties, and then we're going to do it another kind of more streamlined way, which is totally equivalent in the way I usually approach them, because I think it's a little bit easier. But it begins with factoring. Both approaches begin with factoring, 25 times 3. Now, if I'm doing it the first way, I stop there and I say 25 times 3, and the reason I stop there is because 25 is a perfect square. I'm hunting for perfect squares. And then I use that property that says, well, I can split up a radical over multiplication, and the square root of 25, I know that one, that's 5, times root 3. This approach, it works well enough. It does sort of count on us recognizing squares when we see them, though, and knowing them, and that works. It's all well and good for 25, but once you get up to like 169 or 289, maybe it becomes harder to recognize those values. So this works regardless of whether you know your squares or not. If I take 75, what I do is I start out factoring, but I go all the way. So I break that 5 down into 5 times 5. And then I write it out, 5 times 5 times 3. And if we're simplifying a square root, what we want to do is look for pairs of the same factor. 2 of the same factor inside becomes one single factor outside. So this is 5 root 3. Of course, we get the same result, as well we should. But this is usually, like this second approach is usually how I come at these simplifying problems. It doesn't require me to recognize perfect squares. I just need to know how to factor. And I'm pretty good at that, I guess. Now, here we hunted for the 2 of the same factor inside. We did that in particular because this was a square root. That little number that we write in the crook of the radical sign, we call that the index of the radical or the order of the radical. And when there's no index written, it's assumed to be 2. We see square roots all the time. But then we have to specify when we're using a different index. So we always write the 3 if it's a cube root. Whatever that index is tells you how many of the same factor inside you need in order to bring one out. So now let's try to simplify this. This tells me that maybe I need 6 whole factors of something inside in order to bring one outside. Now, you might be looking at this and thinking, 8 is 2 cubed. I have at most 3 factors of 2. In fact, I have precisely 3 factors of 2. Why don't we just give up? I'm not going to do that. I would never give up on this. So what I'm going to do is say, well, 8 is 2 cubed, right? I'm just going to write it in its exponential form. And because I know that radicals are just exponents themselves, how could I write this 6th root of 2 cubed in its exponential form without using a radical notation? Two to the 3 over 6. Yeah. And of course, 3 over 6, we can reduce that. That's a fraction. 3 over 6 is a fraction equal to a half. So as it turns out, the simplified radical is the square root of 2. Now, these 2 examples that we did illustrate a couple of the key things that we're looking for when we simplify a radical. One is that, yeah, we do want to purge the radical from any perfect squares or the cube root from any perfect cubes, right? Like we want to make sure we take out any factors we can take out. But the other thing we want to do is express that radical using the smallest index possible. So the 6th root of 8 was not simplified because we could express this as a smaller index, a smaller order radical, as a square root of 2. And you can actually convince yourself that these are equal. Let's just have a go at this. The 6th root of 8. So this gives us a nice decimal approximation. You might recognize that already, but if we find the square root of 2, they give us the same thing. So those 2 examples really just illustrate these 2 things that we're angling for when we're trying to simplify a radical. Now, in this example, this is the square root of a cubed b squared. We're not going to reduce the order of that radical, unless what we had inside was like a perfect square itself, and we can get rid of the radical altogether. You know, if you're looking at square root, you're not going to reduce that order. So right now, we're looking to eliminate perfect squares. So a cubed is a squared times a, and then we have b squared. I chose to write a cubed as a squared times a because I look at this, say, oh look, there's a perfect square, and there's a perfect square. So what are we going to write for our answer here, our result? AB times the square root of a. Yeah. Another? Might as well. Okay. All right. This is a 9th root. At best, I guess we could say, well, we have a y to the 12th, so certainly we could take out a factor of y. But the other thing I want us to observe here is that our exponents, in fact, let me do one thing to rewrite. The 27 is a perfect cube. We have 3 cubed, x to the 6th, y to the 12th. Those powers inside the radical, 3, 6, and 12, they're all multiples of 3. The index of this radical is also a multiple of 3. So that's going to afford us some ability to simplify this. Let's see. Let's utilize that exponential form. So I'm going to take this 9th root and write it as a 1/9 power. And once we've done that, we can distribute that exponent. So we have 3, let's see, if we distribute to 3 times 1/9, 3/9 x to the 6/9. I'm distributing and multiplying all in one go. Are we all right with that? Okay. Let's reduce these fractions. So we have 3 to the 1/3, x to the 2/3, y to the 4/3. And now look at this. These denominators are all the same, which means I could write this all in a single radical, all in a cube root. Now if I write this in a single cube root, what goes inside? Times y to the 4th. Now that y to the 4th, I'm going to write that as y cubed times y, because now I'm going to go ahead and take out that factor of y we were observing before. So I've got a perfect cube inside a cube root. So we have y times the cube root of 3x squared y. A quick note about kind of notation and just good habits to get into. If you're writing, the index, make sure it looks like it's inside the little crook of the radical, because otherwise you don't want it to look like we have a y cubed sitting out here. Also, when you do pull out a factor, it's generally recommended that we write it on the left side instead of on the right side, because otherwise when you're going along writing, it could easily, if I wrote times y over here, it could look like maybe the y was inside the radical. These aren't like hard and fast rules, but they're kind of conventions to help make our work easier to read. More. You guys are worried we'd run out of material. I knew we'd be all right. So we don't like seeing radicals in the denominator of a fraction, and we don't like seeing denominators inside a radical. So here I have a fraction inside a single radical. Now this isn't a cardinal sin of mathematics. I don't want to phrase it that way at all. If we're doing is expressing a numerical radical, it is considered unsimplified, but it's not like, it's more of a convention than a hard and fast rule. For the purposes of this course, though, when I say simplify the radical, it does include the fact that we need to rationalize denominators. So we don't want to have these denominators in the radical or radicals in the denominator. Our first step is to write it as a ratio of radicals instead of a ratio inside a radical. Now the square root of 2 is just fine, right? I have no problems with having radicals up top. The problem is the square root of 5 on the bottom. We want to fix that. Does anybody know how? Anybody remember how? We talked a little bit about this last semester, briefly. Yeah, like the square root of 5 is what we want to fix. So we'll multiply the top and the bottom by the square root of 5. Now, this is a square root, and the reason we chose to multiply by the square root of 5 is because you need precisely 2 of them just to get rid of the radical to end up with 5. If it were a cube root of 5, I'd need to multiply by the cube root of 5 squared. I need 2 more factors of the cube root because I want 3 factors of the cube root of 5. So root 5 times root 5 is 5. Up top we have the product which we can write a product. We can combine a product under a single radical. So we got root 10 over 5. Can I reduce that fraction? No. Can you tell me why? Yeah, and the 5 is not, right? So we can only cancel common factors if I have, like, if both numbers are inside a radical or both numbers are outside a radical. So the 5 is not a radical, the 10 is. We don't have a factor of 5 up top. We have a factor of the square root of 5 up top. Now, this one is similar. We have a radical in the bottom. We want to get rid of it. And if your instinct is to say just multiply by the square root of 18, that's fine and it will work just fine. Sometimes our work can be a little bit easier if we simplify the radical first. So 18 is 9 times 2, which is 3 times 3. So this is the square root of 3 times 3 times 2. We have a pair of 3's we can take out. Now, having simplified it in this fraction, the only problem is that square root of 2. The 3 is fine. That doesn't bother me at all. So all I really need to do is multiply the top and the bottom by the square root of 2. When we do that, up top we just have 5 times the square root of 2. What do we get on the bottom? 6, yeah. Because this, of course, gives us a factor of 2. Can we reduce that fraction? No, because the 2 is inside a radical and the 6 is not. One additional bonus. You guys were afraid we'd run out of material. I knew we wouldn't. Bonus example before we do that last one on the back. Let's say I wanted to simplify this, 1 over the cube root of 9. Well, the first thing I would do, I'm just going to factor this 9 as 3 times 3. The radical itself, the cube root of 9 is simplified, right? I got no perfect cubes that I could take out. But if I want to get rid of this cube, what factor would I need to throw in? Like, what would I multiply the bottom by in order to get rid of that cube root? Say that again?
Cube root of 3.
Yeah, the cube root of 3. Just one cube root of 3. What I'm trying to do is create the situation where I have precisely 3, or a multiple of 3, factors of the same factor inside this cube root. This already has 2 factors of 3. So I need just one more. And when we do that, this, of course, just gives us 3. And up top, we have the cube root of 3. I keep doing this. I'm not sorry, by the way, but I'm going to do one more bonus. Let's say, sorry, I know it sounded like I was being a jerk when I said I'm not sorry. What I mean is you're welcome, because we're getting more practice, more examples. Let's say I want to simplify the cube root of 12. You know, I'm going to start out very much the same way, right? We're going to factor it. 12 is 2 times 2 times 3. We know we're going to multiply by some cube root. What factors do I want to include here inside this cube root in order to rationalize? Two times what?
2 times 3 times 3.
Times 3. Yeah, so we picked up just one factor of 2 because I already had 2. I only needed one more to bring myself to 3. We started out with just one factor of 3, so I needed 2 more to end up with 3 factors of 3. So same thing up top. So up top we have the cube root of 3 times 3 is 9 times 2 is 18. And what do we have on the bottom? 6, yeah. Because we have, like, the cube root, we have, basically, if I wrote it as a single cube root, we'd have 2, times 2 times 2 times 3 times 3 times 3. So we have a factor of 2 and a factor of 3. All right, so we have 6 overall on the bottom. Let's test this out. Let's take 1 and divide it by the cube root of 12. And we get 0.436 something, blah, blah, blah. And now let's do the cube root of 18 divided by 6. Oops. Beautiful. You love it? Is it almost as good as graphing trig functions, you guys? Better? Wow. I figured that would be tough to beat. You're like, nope, not at all. All right. What makes this problem annoying for us? Annoying and or interesting?
Got a fraction and a radical.
We have a fraction under a radical. What else?
Negative exponent.
Which is also a fraction under a radical. But yes, you're right, negative exponent. What else?
A and B.
That we have 2 variables? Sure.
Addition.
Addition. We can't go off half-cocked now splitting up this radical. We simply are not allowed to do it. We have to be careful. We have to realize that really what we have going on inside this radical, we see one fraction they at least had the decency to write as a fraction, right? The other fraction they try to hide by using negative exponent. So we're going to fix that first. And when we write that as a fraction, it's 2 over b squared, because of course the negative 2 power is only on the b, not on the 2. We're flipping the b, as Alex said.
I should have thought about that a little.
No, that's all right. Okay. Now what?
Add the fraction.
Yeah, I mean, now that we actually have it written explicitly as a sum of 2 fractions inside, may as well do the addition. It's really the only option that's open to us. No properties of radicals or exponents are left for us to use here because of that addition. So the first fraction needs to pick up a b squared. The second one needs to pick up a 2a squared, because of course these denominators are relatively prime. They share no factors in common. Now our common denominator is 2a squared b squared. Up top, we have b squared plus 4a squared. Why is this not simplified? I mean, we made progress for sure, but it's not the addition, really. That's the problem.
Is it that we're sharing variables both in the numerator and the denominator?
Nope.
Get rid of the a squared.
Yeah, sort of. How? First of all, which a squared? Nope. So we have to be, the addition that we've got is in the numerator. So we have to be really careful about that. But the operation that we have that we can use our rules of exponents and rules of radicals on, we've got division. And this is not, the reason this is not simplified is because we have a denominator inside a radical, right? We want to rationalize this this expression. So I'm going to split up this radical. And really, there's no way, like if your mouth is watering, like just looking at the top, like wondering, like, oh, I gotta be able to do something with that a squared or b squared. Nothing we can do. The addition just ruins it all. But let's just walk it off and focus on the bottom. Because you know what's great about the bottom? Multiplication, right? Like, they're all multiplication. Let's pull stuff out. What can we take out? An A and a B. Yep, we can take each of these guys out. So we have on the bottom now AB times the square root of 2. This still isn't quite simplified. Can somebody tell me why?
You need to rationalize.
Yeah, we still need to rationalize. But having pulled out the A and the B, the only issue now is the root 2, right? That's the only thing we need to fix. Exactly. So let's hit the top and the bottom with the root 2. On the bottom, we just have 2AB. On the top, we have a product of two radicals, so we know we can combine that as a single radical. I'm going to leave it written as a product, so 2 parentheses b squared plus 4a squared. Just write it like that. That is about as simplified as this is going to get.